Pamela, Abshire. I'm here to talk about large area low noise SPADs and standard CMOS. So there was a fortuitous coupling of the two, the previous paper and this one. Perhaps I can skip some of the background. Okay, so SPAD detectors we're interested in as sensitive, low-cost light sensors. The basic mechanism is that they, as most semiconductor sensors, have electron hole generation from photon absorption, that you have a high field to accelerate those carriers, which create an avalanche process generating more carriers. So beyond some threshold bias, you have an avalanche process. In Geiger mode operation, as we've just seen, you can achieve photon counting. Functionally, once the avalanche starts, you've detected one photon or one thermal event, and then you need to reset, quench the diode, reset the diode to start again. So one of the key things is to be able to one of the key advantages of doing SPADs with CMOS is that you can locally integrate quenching and recharging circuitry. So this is just some traces to show you SPADs. This is background. I wanted to start with just setting the stage with some prior work that we've shown, my lab has shown with SPADs and standard CMOS. As we've just heard a good demonstration of, the challenges for making SPADs and standard CMOS are the perimeter breakdown, which gives you a large high dark count, and because when the perimeters are breaking down, you have a low photon, so your perimeters are breaking down, so you're not getting volumetric breakdown, so you end up with a low photon detection efficiency. The two methods that my lab has previously investigated for trying to achieve this volumetric breakdown, which is really what you're after, is this method for lateral diffusion of N wells, which I think is very similar to the method that we just saw, and also we've also introduced the control gate over the junction periphery. So if you put a polygate, a control gate, and use a field-induced suppression, that's also an effective method. Okay, so we had a paper in Sensors Journal in 2010 to show these two effects. So one thing to just note is with no gate voltage on the polygate, so without the field suppression, there is this intermediate range of N-well spacing in order to get that slightly lighter doping at the edge that gives you some suppression. But what we find is that the polygate in all cases gives much better suppression. And so going forward from this work of ours, we have actually dropped the N-well approach, and we only use the polygate approach now because because for all values of N-well with no spacing even, you get as effective a suppression with the field-induced peripheral suppression as with using the N-wells. We subsequently showed more recently, so that was work showing essentially that you could just suppress dark count, which is important, but as you suppress dark count, there's always the possibility you're going to be suppressing your ability to detect signals at the same time. So we went back and looked at, as a function of that peripheral gate voltage, the dark count rate and the detection rate, and we found that as a function of that peripheral gate, you could essentially use the bias on the peripheral gate to tune your signal-to-noise ratio and get a 2 orders of magnitude increase in signal-to-noise ratio using this peripheral gate. Of course, we are decreasing the dark count rate, so by imposing the peripheral field-induced suppression, we decrease the dark count rate substantially. This is showing down to a couple of thousand hertz for this pixel, which I believe was about 600 microns square. This shows that at the same time that we're suppressing the dark count rate, we're impinging on some of that volumetric area at the edges, so we lose a little bit of our signal, but at the same time we have an overall win because we've reduced the noise so much. Okay, so now that's the background. We're going forward here to show you what we're doing with trying to get large area low noise SPADs. The challenge, of course, is that in CMOS we want to have the detectors coupled with circuitry. In order to put the circuitry along with the SPADs, you're always going to face some sort of degradation of fill factor. If we want to get back fill factor, we have to put in larger devices, but putting in larger devices brings back the problem of dark current. In many modern SPAD designs that you see reported, the pixel size, the active area, the photoactive area is less than 100 microns, significantly smaller than in a lot of devices. The dark count is always there, arising from those thermally generated carriers and degrading the sensitivity. What I'm going to show you today is that we've developed some new device geometries that allow for more effective gettering and annealing that reduce defects in the active area just in the course of the fabrication process, allowing impurities to diffuse outward from the center of the active regions. What I'm going to show you on the next slide is this capsule-shaped geometry that allows better diffusion of those defects so that we can have much more effective suppression of dark current. So the three devices I'm going to talk about today are this classical SPAD design that we've seen, which is essentially what you've seen before, but without the end-well. So this is just the SPADs that we were looking at before, but we've stopped using the end-well because the polygate does it just as well. And then we have a couple of stretched geometries, both with a 1200 micron square area. The kinds of characterization results I'm going to show you are for breakdown and for dark rate configuration. So when we're doing IV sweeps, just to characterize breakdown as a measure of how effective the peripheral breakdown has been suppressed, we're using essentially a bare SPAD with no additional circuitry, just connected to external instruments. When we're characterizing the dark count rate, we're actually using this we're using the SPAD in conjunction with local active quenching and resetting circuitry and just taking transient traces off the chip. Okay, so the IV characteristic, this is for this, not the long and skinny one, but the kind of the short fat cigar shape. Okay, this is the IV characteristic I'm showing you for the device 3. The inset is the device characteristic for the original circular device. So what you can see is for the original circular device, this is as a function of the voltage across the diode for different values of bias on the peripheral gate. And what you see is that at some point, once you get enough bias across the diode, you get breakdown. That as you increase the voltage on the peripheral gate from 0 volts up to 18 volts, you increase the voltage at which breakdown occurs. So we've quantified that voltage at which breakdown occurs as the diode bias, the reverse bias voltage, at which you achieve maximal slope. Okay, so for any family of curves like this, we can now characterize what the breakdown voltage is. Here is that IV characteristic for device 3, the short fat cigar. And the thing to notice here is that still it's essentially the same range of reverse bias voltages, but the range of gate voltages for which breakdown is for which we've kind of effectively suppressed the peripheral breakdown is significantly smaller. So in the circular structure, we were requiring voltages of up to 16, 17 volts in order to get effective suppression of the peripheral breakdown. In the cigar-shaped device, we're getting that same effective suppression at about 13, 14, or even less. Okay, so here's the breakdown voltage characterized for those 3 devices over as a function of the gate bias voltage. This is that peripheral gate voltage that suppresses the breakdown. So for the circular device, you can see you're kind of slowly coming up, and you'd be out here somewhere if you wanted to see effective peripheral suppression to get to the volumetric. But for the 2 cigar-shaped devices, we get pretty good peripheral suppression at significantly lower gate bias voltages. Okay, so the take-home message here is that these geometries actually allow for better suppression of the peripheral breakdown because they're allowing for the for better defect density. Okay, and here's just a trace. So now I'm switching from the IV measurements using a bare device to Geiger mode transient responses, and I'm going to show you some dark count measurements. So this is the dark count rate. So now we're going back to the active circuit where we've got active quenching and resetting locally. Okay. Okay, and so now this is just showing, a trace from that circuit. This is, sorry, a transient trace from that circuit where we have quench and recharge mechanisms locally. In this case, our event pulse width is on the order of 150 nanoseconds. It's not as fast as some of the circuits that are reported in literature. This is implemented using a 0.5 micron CMOS process. I imagine the same as the one we saw in the previous talk. Okay, so this is the data that shows dark count rate in counts per second as a function of gate bias voltage. So the gate bias voltage here is a mechanism that we're using to suppress the peripheral, the peripheral breakdown. And what you see, so this is focusing only for the moment on devices 2 and 3. So go to the inset for a second. So the inset actually shows the dark count rate as a function of the diode bias for different values of the gate bias. So what you see when you look at the dark count rate as a function of the diode bias is that as you increase the voltage across the diode, you get more dark counts. Okay? For higher value of the gate bias, that peripheral gate bias that's suppressing the breakdown, you get lower dark count. Okay, so now what I'm showing you here is swapping that, and so now the axis that's being swept here is the axis here that's between these two different curves, and we're fixing the voltage across the diode at either 16.5 or 17 volts. Okay, and so this is the trace for 16.5 volts diode reverse bias. This is a trace for 17 volts diode reverse bias for devices 2 and 3, which are essentially have very similar results. Okay, so when you have a little bit more diode bias, you get a higher dark count. Okay, that makes sense. When you have a lower reverse bias across the diode, you get a lower dark count. And what we're showing is that up to gate bias voltages of 11 and 12, we're showing less than 10 hertz dark count rate. And this is on a 1200 micron square device. So I'll summarize now. So from prior work, we've already seen that the peripheral gate suppresses perimeter breakdown. Active quenching and recharge circuits can give fast temporal response, where fast is relative to whatever technology you're working in. The perimeter gate bias increases signal-to-noise ratio, so it decreases your dark count rate substantially. At the same time, decreases your photo collection a little bit, but overall, there's a big win in signal-to-noise. What we're showing now is that this capsule-shaped geometry that we just started working with effectively suppresses the perimeter breakdown, and at the same time gives unprecedented low dark count rates that we haven't seen elsewhere in the literature. The perimeter breakdown is suppressed at a much lower voltage than in the comparable circular devices, so we think that's a good indication of that we're achieving volumetric breakdown, and that it's an effective structure for doing that. At the same time, the dark count rates are less than 10 hertz, which we haven't seen reported elsewhere. The circular device, or a previous version of the circular device that we worked with, that was the device we were reporting the signal-to-noise results for, was giving us about 1300 hertz dark count rate for a 600 micron square device. Other results, the lowest result I've seen in the literature is about 50 hertz for a 50 micron square device. So we're well above that in area and well below that in dark count rate. I'm happy to take questions.